In today's world of telescopes, man-made satellites, and animated videos of flying among the planets, we take for granted the three-dimensional visual space of our solar system and beyond. But this understanding does not come from the senses, and it's possible only with a physical hypothesis of the underlying motion. So let's take a trip back in time to the world of the astronomers of ancient Egypt and Greece. What did their observations show them? It is difficult today to have the opportunity to truly see the splendor of the night sky, free from light pollution. In the darkness of a moonless night, the human eye can become sensitive to even very faint light, and the starry sky is wonderfully full. Let your eyes adjust to see the sky of 2,000 years ago. Now let's have a seat and watch the stars as we talk. During the night, this is what we see. The stars move. Some more, some less, and one hardly at all. It appears just as though we are watching the rotation of a very large sphere around us. We'll watch through the night again, this time with markings to indicate the circles the stars seem to travel upon. Based only on this observation, the simplest explanation is that we are surrounded by a sphere of stars, which move around us just as the sun does. Now we'll turn around and face away from that star that didn't move, and we'll watch the night several times in a row. Each night looks almost the same, but there are differences. See what you can spot. I bet you noticed that the moon changed. The first night, it was a quarter moon, and was already halfway through the sky when dusk made it visible. The side of the moon that is bright is the side facing the sun. 1 week later, it's full, and it comes into view nearly opposite the sun, just rising as the sun sets. During each night, the whole sky moves to the right as we face south, but the moon appears to be moving more slowly. The moon doesn't keep up with the stars in its neighborhood and lags behind them. Even during one night, it moves slowly to the left, although this is hard to see. The moon cycles through its phases again and again, once every 29.5 days, creating the period of time that we call the month. It's not a coincidence that the words moon and month are similar. They have the same origin. Now let's look for another difference, one that's harder to spot. We'll watch sunset for the first night, and then 1 week later. Did you notice any difference? If we consider the sun as our point of reference, the stars seem to move to the right. Or if the stars are your reference, you could say that the sun moves to the left, that the sun didn't move as quickly as the stars every night, and lags behind them, like the moon, but much more slowly. Now you see a time-lapse sequence of a whole month of sunsets. The sun is moving against the stars along a particular path. Obviously, unlike the moon, we can't directly see which stars the sun is near, since we can't see any stars when the sun is out. But if we had a star map created by our minds and recorded or devoted to memory by some means, we could map out the path of the sun by relating it to the stars we do see. Hipparchus famously created the first star map, recording the position and magnitude of 1,000 stars in the 2nd century BC. With such a map, it was possible to map out the position of the sun against the stars. The sun's course along the stars forms a circle and returns to its beginning over the course of 1 year. This path is called the ecliptic, and there are 12 special constellations of stars along this path, the 12 constellations or signs of the zodiac. In case you've ever wondered what your sign is, it means the constellation the sun is in when you were born. When such work was first done in the Mediterranean, the sun was in the constellation Aries on the day of the spring equinox, the start of the year. This name has stuck, and the position on the ecliptic, where the sun is located on the first day of spring, continues to be called the first star of Aries. The position of the sun at the spring equinox actually moves along the ecliptic in a 26,000-year cycle, such that it now occurs in the neighboring constellation Pisces rather than Aries, and it's nearing Aquarius. So when you look up what sign you are and compare that to where the sun actually appears on your birthday, it is one sign off. This 26,000-year cycle was discovered by Hipparchus. So now, back to the motions we observed. The overall motion of the entire heavens, going to the right as we face south, is called the first motion, while the relative motion of the sun and the moon to the left, against the stars, is called the second motion. This second motion, from night to night, can only be seen by the mind, not the eyes. Actually, even the first motion of the stars is so slow that you don't really see the stars move during the night, unless you're using a telescope or binoculars. Instead, you notice that their position with respect to the horizon or another landmark has changed over the course of the night. Now we'll look for another change in the sky from night to night. We'll direct our attention to a very particular bright star in the sky. Now, we'll look at this exact patch of sky the next night, and the next, and the next. Over the 10 days shown here, this one star is wandering from place to place in its second motion. It is from the Greek word for wanderers that we have the word planets. In this case, the wandering star you see here is known as the planet Mars. This slow motion could only be studied in a thorough way by a civilization making frequent and systemic observations of the night sky over many years. The bewildering motions of these few wanderers, only 5 visible to the naked eye among a sea of fixed stars, were, and continue to be, the cause of wonder, curiosity, research, discovery, and not infrequently, exasperation. Well, how were they studied? Earlier, I mentioned Hipparchus's catalog of 1,000 stars. How do you think he measured and mapped the locations? How do you draw a perceptual sphere of stars on a flat piece of paper or stone? Or, if you were to record positions as numbers rather than a drawing, what are your reference points? What do you measure? How would you keep track of the motion of one star among many over a prolonged period of time? Now we'll watch Mars over a number of years as it traces out its path in the heavens. In this video, I have cheated by removing the Earth and its atmosphere so we can see stars during the daytime without the sun washing out the entire sky with its light. Now, as you see, the motion, the speed of Mars is changing dramatically. It speeds up, slows down, and even goes backwards. For the most part, it stays very near the ecliptic, that course traced out by the yearly motion of the sun. So what are some of the basic observations we might make about this motion? Well, first, we could measure how often Mars makes its loop. We could also see, on average, how long it takes Mars to return to the same position against the stars. Now, such observations themselves don't tell us what's physically happening out there. What would you think if you were living 2 millennia ago? Are the stars moving on a sphere? Is Mars? Is Mars closer or farther than the fixed stars we measured against? And how far away are they? From these observations, how would you suspect that the moving stars, the planets, are bodies like our own Earth? Or that the Earth spins? Or that the planets move around the sun? In the next video, we'll jump ahead to Kepler's day, and we'll compare 3 different hypotheses for the motion of the heavens.